Hello there, my name is Gabriel Aviles Cordero. I'm gonna be presenting Phase D of Capstone 2 project, titled Continuous Passive Motion Device Mechanical System. The presentation outline consists primarily of a system validation, a project plan, and finally, a system budget. To start, let's talk about our validation objective. First, our aim for the Capstone project is to manufacture a resilient and affordable continuous passive motion device or CPM device with the capacity to facilitate flexion and extension for the knee and dorsiflexion and plantar flexion movement of the ankle. Additionally, the objective of the phase is to validate our MOPs presented in previous presentations. Before specifying and talking about our validation methods, we have to talk about our project amendments. Due to the lack of capital and material resources, the decision was made to make changes in the materials and pulley size. Within this project, we will be using a teaming pulley system. Teaming belts are made of rubberized fabric coated with a nylon fabric and it has steel wires within to take the tension load. It has teeth that fit into grooves caused in the periphery of the pulleys. A teaming belt does not stretch appreciably or slip and continually transmit power at a constant angular velocity ratio. No initial tension is needed. Such belts can operate over a very wide range of speed, have efficiency of a range of 97 to 99%, require no lubrication, and are quieter than chain drivers. There is no quarter speed variation as in the chain drives, and so they can attract solutions for precision drive requirements. The selected designation is at XL. XL means that it has a 1 divided by 5 pitch. This is due to its increased load capacity and cracking resistance. Additionally, per manufacturer specification list, it is suitable for office machines, machine tools, postage equipment, sewing machines, vending machines, outdoor power equipment machines, food processing, wood cutting machines, papers, and sand application, amongst others. In the bottom corner of the page, we can see a table which tells all the teaming belt specification and standardized size. And in the right corner, we can see the XL specifications and standardized size, specifically the XL one. Going back to our project amendments calculation and assumptions, we selected a DC motor for the knee system with an inlet torque of 4 newtons meter, an inlet angular velocity of 1000 RPMs, and a constant or volt consumption of 12 volts and 2.5 amperes, a motor potency of motor power of 30 watts. We also assumed the diameter of pulley 1 to be 1.401 inches. We also wanted an output or angular velocity output of around 300 to 400 RPMs. We needed an outlet torque of 14 newtons meters, and we designed a center distance between pulleys of about 5 inches. Now, to calculate our diameter of pulley 2, we calculated the pulley 2, saying that diameter of pulley 2 equals diameter of pulley 1 multiplied by initial angular velocity, and all that divided by output of angular velocity. That gave us a diameter of pulley 2 of about 4.6669 inches. Also, we calculated the contact angle which contact angle 1 gave us as a result of negative 29.523 degrees. Contact angle in pulley 2 should be of 35 degrees 0.812. For our belt length, we calculate a belt length of 20.065 inches with a belt velocity of 74.5354 inches per second, or 1.858932 meters per second. Knowing the diameter of pulley 1 and pulley 2 as was previously defined, we then start defining the desired angular displacement at 150 degrees. Also, we wanted that speed to be roughly 150 degrees per minute. In other words, we wanted to roughly that the process of cycle took around 1 minute or 2 minutes max. We then start to convert our angular displacement to our linear displacement by means of sine law, in which we stipulated that our line A should be, or position A, or segment A should be 24 inches long, and segment B should be 19 inches long, with a degree of 80 degrees of displacement. Using sine law, we obtain a linear displacement of 27.904 inches. The movement will be carried out by threading produced by having a lead screw rotated into its own x-axis. The information of the description of the lead screw is as follows. The length should be around 120 centimeters, of which 70 or 80 will be used, but we will have the speed and displacement calculation about 96 centimeters as precautionary measurements to have additional space. The diameter of the lead bar will be around 0.5 inches or 1.27 centimeters. It is stipulated as a screw pitch 0.5 minus 10, 1 pitch, or 0.100 leads, which means that which indicate the distance between teeth, meaning that it will have 10 teeth per inches or 10 hoops per inches. We converted the linear displacement into revolution per minute on the bar breathing, and we obtain a roughly lead angular velocity of 310 RPMs, which coincide with the output that we wanted. For our ankle system, the flexion of the deflection range of motion cover an area of roughly 80 degrees maximum. For the flexion, we must have a maximum of 30 degrees, roughly 20 degrees in average. And for the dorsiflexion, we have a maximum of 50 degrees. The point of origin to be considered is a perpendicular intersection, or 90 degrees. We assume a 1.17 Newton meters torque motor. Base force is lower and the maximum force on ankle can exert 2 newtons. The selected value is intermediated when assuming that the ankle joint will not be forced. The mechanical system used in the project is a modification of a previous CAD design by Sakid Muhammad. In the design, the mechanical system used a bevel gear. This type of gear are classified as follows: straight bevel gear, spiral bevel gear, swivel bevel gear, hypoid, and spheroid gears. Our design is a straight bevel gear, which are usually used for pitch line velocity of around 1,000 feet per minute or 5 meters per second, or but can be used as lower, when the noise level is not as important consideration. They are available in many stock sizes and are less expensive to produce than other bevel gear, especially in small quantities. The design used provide us with a bevel gear 1. We have a quantity of 16 feet, and a modified bevel gear 2 they have a quantity of 24 feet. As mentioned above, the range of motion of the angle of interest is 80 degrees max. According to the given design, bevel gear 1 has a diameter of 1.5 inches with a number of teeth of 16. On the other hand, bevel gear 2 have a count of 24 teeth. Therefore, the gears ratios is given as 24 divided by 16. We have a gear ratio of 1.5 or 0.66667 to 1. Therefore, we can say the following. Stipulated with a motor torque of 12 kilograms per centimeter or 1.70 newtons meter, traveling a max of 80 degrees, and using a servo motor programmed to only move specifically to that degree, we can say the following. At 6 volts, the angular velocity of the servo motor will be 0.22 seconds per 60 degrees, as programmable to 80 degrees per 8 seconds. With an initial angular velocity of 11.27 degrees per second, or 1.8783 RPMs, given the gear ratio, we can use the obtained information to define the output torque on the output angular velocity. We have an output angular velocity of 1.8783 RPMs multiplied by 0.66667 gives us an output angular velocity of 1.22529 RPM. Our torque or output torque is of 1.7652 newtons per meter. Having finished our project amendments, now we're going to talk about system level measurement of performance, or MOPs, to be verified or validated. Our first MOP is the torque output need, which should be around 13.4 newtons meter. Our torque output angle that should be around 1.7652 newton meters. Our range of movement for the ankle and knee, it should be 2, or freedom of movement to be exact. Our motor power in the knee should be around 65 watts. Our motor power ankle should be around 0.3 watts. The motor velocity output in the knees should be, or the input should be around 1000 RPMs with a motor capacity of 13 RPMs max. A motor velocity in the ankle should be around 1.87 RPMs. The operational weights of this mechanical system should be less than 8 pounds. The investment cost should be no more than $100. In the knees, we have a $50 max and ankle $30 max. And lastly, the range of movement should be 120 degrees or 150 degrees for the ankle, for the knee, and 80 degrees for the ankle. Our first system validation or verification procedure is to the torque output of the knee. The safety precaution is that the system don't exceed the stall current of the DC motor and take the necessary precaution not to burn the battery. Tools to be used: Manufacturer motor specification. Motor Titan 550-21T 12 volts DC motor. Arduino 1. RC control, power supply, transmitter, tachometer. Manufacturer motor specification as said previously, calculator, and different weight pieces. In the procedure from the validation, first the motor will be placed in its proper location to begin its cycle. Once the station location is established, several cycles will be run with various loads to calculate its torques. With a tachometer, we will measure the true speed of the output pulley and its corresponding load weight. We write down the RPM load data and formulate the linear graph to observe its behavior. The DC motor are supposed to demonstrate a linear behavior in relationship of angular velocity and torque. This will help us identify the relationship between speed and torque output. We're also going to calculate the torque using the weight of the load and the distance of the pulley, or the radius of the pulley. To validate our objective, we're going to observe the relationship of the linear relationship of the torque and RPMs. If it demonstrates a linear behavior, then the objective is validated. As also, we're going to demonstrate this to the max load mentioned of 20 newtons meter. Our second verification procedure is to torque output ankle 1.76 Newton meter validation. Safety. Similar to the first MOP, don't exceed the stall current of the motor and take the necessary precaution not to burn the Arduino this time. The tool to be used are manufacturing motor specification, a servo motor power hobby, 12 kilograms per centimeter torque, Arduino 1, transmitter, RC controller, calculator, tachometer, and weights. For procedure, for the validation of the ankle output torque, the specification given by the engine manufacturer will be used to acquire the output torque information after cycling. Various loads will be placed in the forest to measure the different torque experience and to confirm the manufacturing maximum torques. Our third verification procedure is the degree of freedom. Our safety precaution does not apply. The tool's manufacturer motor specification, a 1080p camera, tripod stabilizer, Kinovea software, Windows 8, Windows 11, Intel 5 HD Graphics Surface Pro 6, masking tape or any tapes, station area of 5 feet per 5 feet. Procedure. Place the device in the designated 5 feet per 5 feet area. Position video camera 1080p resolution perpendicular to the CPM to record its movement. Take the video of the entire cycle of the device and save the video. Make note of the observations. Use the Windows 11 computer to access Kinovea program. Kinovea allows us to perform kinematic and statistic analysis, validate the degree of freedom identified in Kinovea with expected results. Fourth verification procedure. Motor power of the knee 65 watts. Safety precaution. Don't exceed the motor max potency of the DC and take the necessary precaution not to burn the battery. Isolate the mechanism to avoid physical contact. Tools. Manufacturer motor specifications. Titan motor 550 21T 12 volts DC motor. A motor drive speed controller. Arduino Uno. RC controller, multimeter, power supply, transmitter, tachometer. Procedure. The manufacturer specification will be used to define the motor power. The energy consumption of the motor will be measured at the moment of executing the cycle with the load. In this way, the motor can be validated. And we're going to connect also the motor to the external power supplies, and for then use analyze the power consumption using a multimeter and the power supply. Our fifth MOP to be validated is the motor power ankle of 0.3 watts. Similar to the previous one, don't exceed the motor max potency of the DC and take the necessary precaution not to burn the Arduino power supply. Isolate the mechanism to avoid physical contact with the patient or user. Tools: servo motor power hobby 12 kg per centimeter, Arduino 1, RC controller, multimeter, power supply, transmitter, tachometer. The manufacturer specification procedure. The manufacturer specification will be used to define the motor power. The energy consumption of the motor will be measured at the moment of executing the cycle with the load. In this way, the motor power will be validated. As previously mentioned, the motor will also be connected using the power supplies and a multimeter. Using the multimeter, we then measure and identify the power consumptions. Our sixth MOP to be validated is the motor velocity of the knees, 1000 RPMs, and the safety precaution: rapid, sudden, and jerky movement acts against the rehabilitation purpose of the device. In addition, any sudden and excessive motion can cause injury to the user. Tools: motor Titan 5502110 12V DC motor, Arduino 1, RC controller, 1080p camera, tripod stabilizer, Kinovea software, Windows 11, Intel 5 HD Graphics Surface Pro 6, tape, station area of 5 feet by 5 feet, a transmitter and a tachometer. Procedure: place the device in the designated area. Begin the operation of the device as instructed. Mark the designated point of the output pulley and the output gear. Once marked and all parts are positioned, begin measuring the angular velocity of the proposed part by means of a digital tachometer or a laser tachometer. Additionally, the needle displacement of the extremity will be measured by means of the Kinovea software. The data will be acquired by means of digital cameras connected to computer or tablets. The Kinovea program will allow us to identify what the linear velocity is. The necessary calculations will be made to obtain the equivalent values and the angular velocity of the bars or links. Our seventh MOP to be validated is the motor ankle velocity, 1.87 RPMs. The rapid, sudden, and jerky movement acts against the rehabilitation purposes. Therefore, we have to have safety precautions of the device. Additionally, any sudden and excessive movement can cause injury to the user. Tools: servo motor power hobby 12 kg per centimeter, Arduino 1, RC controller, multimeter, power supply, transmitter, tachometer, a 1080p camera, tripod stabilizer, Kinovea software, Windows 8, 11, Intel 5 HD Graphics Surface Pro 6, tape, and a station area. Place the device in designated station area. Begin the operation of the device as instructed. Mark the designated point of the output pulley and output gear. Once marked and all parts are positioned, begin measuring the angular velocity of the proposed mic by means of a digital tachometer or laser. Also, take the power consumption of the motor by means of Arduino 1 to calculate and specify the speed. The next MOP to be validated is the operational weight, that it should be equal or less than 8 pounds. The safety precautions: Excessive weight of the mechanical system components may cause damage to the system. This is because it can cause overstressing of the actuators and power supply. Additionally, excessive weight can cause deformation of the components. Tools to be used: the servo motor powered Hobby Titan 55021 turn 12 volt DC motor, Arduino One battery, motor controller or speed controller, transmitter, and a digital scale weight. Procedure: first, weigh each of the components that make up the mechanical system. Then, perform a summation of the weights to validate the spec weight of the CPM mechanical system. Follow up: our next MOP to be validated is the investment cost. The knee motor or actuator system shouldn't cost more than $50, and the ankle motor or actuator shouldn't cost more than $30. There is no safety precaution or no applicable tool. It is servo motor power, the Titan 55021T DC motor, and the receipts. Procedure: utilize the stored receipts to validate manufacturing price and commercial price. Find other examples found in these different online stores. Our last verification procedure MOP to be validated is the range of movement that should be 150 degrees for the ankles for the knee system and 80 degrees for the ankle system. The safety precautions: the degree of movement should be kept within the established natural range. Exceeding this parameter may cause injuries to other users or patients in joints. Tools: servo motor, Titan 55021T DC motor, Arduino One RC controller, multimeter, power supply, transmitter, tachometer, 1080p camera, 3-point stabilizer, Kinovea software, Windows 11, Intel 5 HD graphics, Surface Pro 6 taped station area. The procedure: place the device in the designated area. Position the video camera 1080p resolution perpendicular to the CPM and record its movement. Take the video of the entire cycle of the device and save video. Make notes of observation. Use the computer to access Kinovea program. With the Kinovea program, take measurements of the movement and use the software to help us perform a kinematics and statistics analysis. Validate the range of movement identified in the Kinovea with the expected results. Following the system validation, we then enter to a project plan in which we propose bringing an end to our prototype and finishing our capstone to September 1 of the next trimester. The steps to completing or activities to complete the project plan are the system validation. The responsible is Gabriel Aviles. Overall project conclusion, Gabriel Aviles, and overall project recommendation. Next, we present the budget of the project, in which we have Arduino One, manufacturer Arduino, quantity 2, a price of $70. A driven gear, a 3D printer, quantity 1, $0. Driver gear, 3D printer, quantity 1, $0. A driven pulley, Alpha Electronics, $18. Driven driver pulley, Alpha Electronics, $18. A pulley belt of GMB Manufacturing, one quantity, $10. Ankle motor case, self-made, $50. Ankle motor power hobby, one quantity, $50. Knee motor Titan 550 quantity 1, $60. RC controller Traxa 1 quantity 1 $80. Ankle motor piston generic quantity 1 $5. Knee motor piston generic quantity 1 $5. A motor driver speed controller Arma quantity 1 $60 with a total of $426 for mechanical system. I hope you find this presentation enjoyable and useful. Have a nice day.